Right. So at 2r, the gravitational potential will going to be phi, okay, which is just phi at the surface, right, times r is equals to phi 2, which we are interested in, and then 2r, right? So if we simplify, so we will get 2r is equals to this, and r goes off. So phi over 2. Okay. So at 2r, the gravitational potential will going to be half of its previous value at r, right? So if let's say this is 8, so 1, 2, 3, and 4, right? So the point will be right here. Right. So the second point is right here, right? Now, to for the 3r, we can just put back the things in the equation. So phi times r is equals to phi 3 times r 3r, right? So phi over r divided by 3r, okay, is equals to 3 phi, okay? And this gives you 5/3. R and R goes off, by the way. So yeah, and 5/3 gives you 1/3 is basically 0.11, I think. Yes, the 0.33. Sorry, 0.33. So this is going to be 0.33, which means 25%. Okay, 50%, and then 33%. Okay, so this is 50%, and this is going to be 25%, and 33% would be somewhere right here. Okay, and then at 4r, if you want to do the working for, so you'll do the similar working and you'll get 1 over 4, which is 0.25. So right here. And if we draw the graph, so the graph will look like this. Okay, like this. Okay, so this is how the gravitational potential graph looks like around the. Okay, so like at some distance from the surface of the planet, or from the surface of the mass. Okay. Okay, fine. That's done. Now, if we talk about the two masses and the gravitational potential curve, so for the two masses, let me have my mass. Okay, let's say this is the mass, okay, and this is another mass, okay, and I have, okay, the distance between the two masses by, okay, so the distance between the two masses is this one, right? And okay, this is the distance, right? And the gravitational potential at any point due to the two mass is going to be the sum of the potential at the sum of the potentials. Okay, so we can say that potential at any point can be given by the sum of the individual potential division at that point. Okay, so let's say if you're talking about this point, okay, if you're talking about this point, okay. So at this point, the gravitational potential is going to be the sum of the two potential from the two masses, right? And let me just consider the values really quick. So let's say this value is x and the whole value is, let's say, d. Okay, this whole value is d. Okay. Now, so this value will going to be d minus x, right? So if we try to write down the equation for the gravitational potential, the resultant gravitational potential, which you can say that V net or gravitational potential net is equals to potential 1 plus potential 2, because it is a sum of the potential at any point, and then you can just add them, and you can also relate the formula. So G m1 over x my plus with a negative sign, because the formula contains a negative sign. So come on, gm2 over d minus x whole square, right? So, and this is basically the equation for the net potential, okay? And you can simplify it further depending upon the scenario you have given, okay? But if you if you plot the graph, so the graph looks like this. Okay, it will be like that. Okay, and the graph looks like this, like this. Okay. So this is how the gravitational potential graph looks like. Okay, and if you can label the measure axis.
Sir,
Yes,
why
potential
is
should
it d
be on.
minus? Why is
Why
it
is
d
it
minus x square?
not a square? It should just be d minus x.
Oh, okay.
Okay, so over here, there's going to be the potential. Okay, and at this point, there's going to be the distance. Okay, distance, right? So so now you can see that at any one point, the gravitational potential is basically given by the sum of the potential from the individual planet at that point. Okay. So, and this is the overall result or resultant effect. Okay. So, where you have the first planet right here and the other planet at the other side. Okay. And this is going to be the minimum point. Okay. Minimum point. Okay. And this is the minimum point of the graph, okay? Basically, this is going to be the point with the maximum velocity or maximum constant velocity, and after which the velocity start decreasing. Hmm. So, these are basically some of the concept of the gravitational potential. Now, let's just discuss the past papers for the gravitational potential, and the rest of the things are basically done. So, let's see. Let's try some of the question. Okay, Aj. I think we did that in the class. No, we don't. So where it goes. Okay, let me not the ideal system. Come on, it should be earlier. Okay, let's try this one. Just ignore the definition for the gravitational potential. You have to drive this one. Yes. What do you do?
A rocket is launched from the surface of a planet and moves along a radial path as shown in figure 1.1. The planet may be considered to be an isolated sphere of radius r with all of its mass m concentrated at its center. Point A is a distance r from the surface of the planet. Point B is a distance 4r from the surface. So that the distance and gravitational potential delta phi between points A and B is given by the expression delta phi is equals to 3 gm over 10r.
What should you do?
Uh,
You have one point right here and the other point right here, B, right? So for point A, sorry, for point A right here. For point A, you will do the gravitational potential, since we are talking about the gravitational potential. So you can find the individual the gravitational potential at A and at B, and you can subtract them, right? And that will give you this answer, right? Clear? So
okay,
potential
so
at A is basically due to
mine,
this much distance, right? Which is
yeah,
2r. Okay, fine. So when you substitute that in, negative m over 2r. So this is the first value. The second value is, or the second solution will be phi b equals to g, sorry, g into mass, remains the same, and you have the distance of 4r from the surface, so it is going to be 5r, right? Okay, so
yeah,
come on,
it should be
4r.
minus gm now.
Yes, sorry, it should be 5r. Yes. Okay, now since they are asking for the change in the gravitational potential, so you can find the change. So final, which is gm over 10r minus initial, which is 10 over. Okay, ये क्या हो रहा है? So minus gm over 2a, 2r, sorry. So this is the distances, and this is how we can find out the delta phi. Okay, and there's a negative sign as well, so you can solve it. So
How's this 10r?
it's not 10r, it should be 5r. Okay, so now you can take the LCM, so denominator gets 10 and 2gm. Okay, with a negative sign, minus minus plus, and then 5gm, 5gm. Okay, so this is the value. So you can find out the gravitational potential at that point. How much? 3, right? Okay, let's move on to this one.
Yeah, 3.
Hmm.
The rocket monitor is switched off at a point A. During the journey from A to B, the rocket has a constant mass of 4.7 into 10 to the power 4 kg, and its kinetic energy changes from 1.7 TJ to 0.88 TJ. What is
It,
TJ?
it is basically terajoules.
Okay, so into 10 to the power 10?
12, 12.
12, okay.
Okay.
For the planet, the product GM is 4 into 10 to the power 14. It may be assumed that the resistive force to the motion of the rocket are negligible. Use the expression in B1 to determine the distance from A to B.
Okay. So what will you do? The distance from A to B. Okay, let's try. So from A to B. Okay. So from A to B, we can use the law of conservation of energy, where we can say that the total kinetic energy, the change in or the loss in the kinetic energy, because the kinetic energy is getting decreased. So the loss in the kinetic energy is basically the gain in the gravitational potential energy, right? Can we say that?
Yeah.
Okay. So we are saying that the loss in Ke is equals to the gain in GPE, right? This is the first thing. Okay. So the loss in KE is basically 1.7 minus 0.8. Okay. And it is in terajoules. Okay. So everything times it by 1 exponent 12. Okay. Now, this is the first thing. Now, the gain in gravitational potential energy is given by, you can use two formula, either GMM, GMM over R with a negative sign, or you can use delta phi times M. Okay, I'm using the second one was more useful. So, or I can, okay, from A to B, we found out the change in the gravitational potential. Okay, yes, so we can use that. Fine. So change in the potential times M gave me the change in the gravitational potential energy, right? So now, if for the change in the gravitational potential, we can use the previous thing, 3gm over r 10r. So 3gm and then m over 10r. Okay. And we are now interested in, okay, so we know that the second mass m is of this magnitude, the first mass and gm are of that magnitude. So we can use them to find r. Okay. So you can just bring r to the other side and then divide it by, and then divide it by 3. And then gm has a value given 4 exponent 14. Okay. And the other m has a value of 4.7 exponent 4. Okay. And then divided by 10 and then the kinetic energy. So now 1.7 minus 0.88 into 1 exponent negative 3. Okay. So can you please find out for me? Yes, how much?
Just 1 second.
Okay, done.
In I'm getting 146.3.
146.3. Let's see. So, okay, so you are saying you are getting 146.3. So this 146.3 is basically the value of R 146.3. Okay. But don't you think it should be as a, so this should be negative 12 or positive 12, right? Not negative 3.
I
Fine.
I used I used 10 to the power 12 only.
10 to the power 12. Okay, fine. And you put these values?
Yeah.
Okay.
What is 4.7 into 10 to the power 4?
For the mass, this
Oh, I don't
mass,
think I included that. One second.
you have to. Just times the answer by that mass, okay?
Then I'm getting 6878048.
Can you tell me in the standard form, please?
Okay,
S-
6.9 into 10 to the power
Exponent 6 or 4? Yes, the whole
6.
6, okay.
6.9 into 10 to the power 6.
Fine, fine. Now, this is the R, right? And they are interested in finding the distance from A to B, right? And from A to B, the distance is 3R. So you can times it by 3 to get the final answer, right?
Yeah.
How much?
2.07 into.
Okay, 7. 2.07 means 2.1 exponent 7, right?
Yeah, yeah.
Okay, so, okay, fine, that's it. Uh, we'll probably do some more question tomorrow, maybe, or would start the new chapter. Okay, and
Electric field.
probably electric field or probably simple harmonic motion. Depends, whatever going on in your school, we'll start that. Okay,
Uh, Now we're doing capacitance actually in our school.
okay. Then we can start the simple harmonic motion or whatever you want. We can start that. Capacitance required the electric field to be taught, but simple harmonic motion can be done on its own. So, like, yes.
Yeah, can we do simple harmonic motion because it's
Mm.
coming for this midterm
Okay,
exam.
okay.
So,
Okay, fine. We'll do that.
okay,
Okay, sure. Okay, take care. Love is.
love us.
Love is.